This is the faceplate of your oscilloscope. It's what's called an analog oscilloscope, which is the old-fashioned kind. The newer ones are digital, but they're programmable and much harder to use and much harder to figure out what you're actually doing. And so this is much better for people that are just learning how to run an oscilloscope. So this is an Hitachi V212 dual trace or two-channel oscilloscope. And over here is the screen. I've got a sine wave displayed, and you'll be working with sine waves at some point in your lab. And the display is in centimeters, fortunately, and not inches. So each one of these squares is a centimeter. So it's 10 centimeters long and 8 centimeters tall. What we're seeing on the screen is a plot of voltage versus time. And the beauty of an oscilloscope is it shows you what's happening as a function of time continuously. And the time scale can be adjusted, and the voltage scale can be adjusted. So it's kind of a voltmeter that works in real time for a certain length of time. It's a little more complicated than that, a little more sophisticated than that, but we will come to that. So this picture here shows a sine wave, and it has what's called a peak-to-peak amplitude of 1, 2, 3, almost 4, 1, 2, 3, 3.5. So maybe a total of 7 centimeters tall. And we have to figure out how many volts that is. So there's a switch we'll be taking a look at shortly that's volts per centimeter, volts per division as they call it. So that would be 7 divisions roughly, or a little over 7 divisions, and times however many volts per centimeter. If it's 1 volt per centimeter, then that's 7 volts. If it's 5 volts per centimeter, then that's 7 times 5, which is 35 volts peak to peak. The time scale is adjusted by this knob up here, which is the time per division, time per centimeter. That's what divisions are here. Each division is a centimeter, a scale. And so right now it's set on 0.5 milliseconds per centimeter. Now, the human eye can see something new every 30th of a second, roughly. And so if you want to see something that's happening in 1,000th of a second or 1,000,000th of a second, you can use an oscilloscope because it can stretch things out. It can stretch this time scale out so that this whole distance here corresponds to the time of 10 microseconds or whatever you want, 10 milliseconds or 5 milliseconds or a second or several seconds, depending on where you adjust this knob. So it goes from 0.1 centimeters per second. So that would be, since there's 10 centimeters there, that would be 1 second. Take 1 second for this trace to go across the screen. And down here, the fastest rate on this oscilloscope is 0.2 microseconds per centimeter, which means it only takes 2 microseconds to go across the screen from here to here. So that's much faster than you can see, but you can freeze it on the screen like this and see what's happening in a microsecond or a millisecond or some seconds, and take a picture of it or however you want to figure out the data from your display. Okay, so that's kind of a preview of some of the knobs over here. It's a 2-channel oscilloscope. So here's one channel, channel 1, and here's the other channel, channel 2. And of course, they're duplicate knobs and inputs. This is the input to channel 1. This is the input to channel 2. This is the volts per centimeter, volts per division scale. In other words, you can change this, make this look bigger or smaller depending upon how you set this knob. And this is position. There's little arrows, up and down arrows, which means you can move it up and down. This then describes the voltage or the Y part of this display. Likewise over here, this is the input. This is the vertical amplifier adjustment to make each one of these centimeters whatever it says on the screen. You'll notice the 2 red knobs, and you'll notice that they're both turned. You want to check this fully clockwise. When you turn them fully clockwise, and be gentle with turning all these knobs, then they will, at the end, they will click, which means they're in a calibration mode. So the little white line is more or less pointing towards the word calibrate, cal. And so, and again, the arrow indicates turn it clockwise, and that makes it fully clockwise, that makes it calibrated. So supposedly these two are calibrated, and they mean exactly what they say they mean, which is one thing you're going to check, and we'll take a look at that on the screen. Now, there are two switches here, again, same on each channel, AC, ground, and DC, and the difference between the AC, and this will become important when you do your diodes lab. When the switch is switched up to AC, there is actually a capacitor in between the wire here and the screen, physically or electronically, and that capacitor blocks any steady voltage, DC voltage, like from a battery or something like that, from appearing on the screen. So what you're looking at on screen is only the alternating voltage, like the sinusoidal voltage here. And when we flip that down to DC, it lets both the AC and whatever DC might be with it appear on the screen. And you'll see how that's important next week when you do the diodes lab. And then the middle switch is ground. Ground means there's no signal. You can put a signal in, but it's not going to get to the screen. And so if, for instance, if you want to adjust where this is on the screen, you put it on ground, and you will see a line instead of sine wave, and you can move that line up and down to where you want it. Put it in the middle, put it in the bottom, wherever you want it as a reference. So that's what that switch is for. This little section here, we have to talk about the fact that you can freeze this pattern on the screen by adjusting the voltage at which the pattern is triggered to go across the screen. And if you adjust the voltage, say, well, obviously the voltage to trigger it is this voltage here, whatever it is, and when the voltage, input voltage reaches that voltage, it triggers a sweep across the screen. And every time it reaches that voltage, each one of these sine waves, there's one place where it reaches that voltage on the way up, for instance. Then it triggers that pattern, and the pattern looks like it's frozen on the screen. Now, this could be only a millionth or a thousandth of a second, which is too fast for you to see. But if you see it over and over and over again, and it appears to look the same, like it's frozen on the screen, then you can do some measurements with it. It's locked in place, so to speak. So this dial here selects which channel, channel 1 or channel 2, you want to do that with, and which channel you're looking at. So if you switch it on channel 1, you're only looking at this channel. If you switch it on channel 2, you're only looking at this channel. If you switch it on alternate, ALT, then you're seeing 1 and then 2 and then 1 and then 2. And if you switch it on chop, you're seeing 1 and 2 at the same time on the screen. So you can display two different patterns on the screen or two different voltages on the screen at the same time because your eyes retain that image for a long time, and the phosphor lights the pattern up on the screen for a long time, and you can see the pattern frozen. So channel 1, channel 2, alternate, chop, and you can actually add the two. If you switch it to add, it adds what comes in here to what comes in here. That's getting a little fancy. We're going to use channel 1 or channel 2, or I would prefer to use chop because it flashes the same pattern on the screen instead of up, down. It flashes the same pattern on the screen all the time. So it's a little less confusing to use chop. So that pretty well explains this whole part of the panel. These knobs here are for focusing, which is pretty obvious. That is, if you turn this knob, the trace will get sharper or less sharp. So obviously you want it sharp. This intensity knob means how bright it looks. And of course, these kind of go together. If you have it really, really intense, you can't really focus it very well. So you want to compromise by having a pattern you can see on the screen and have it not be glaringly intense, but bright enough to see and able to be focused to a fine line. So you can kind of play with these and get the pattern looking nice the way you want it to look, nice and sharp, reasonably bright, but not too bright, nice and sharp. So that's what those are all about. This little tab here, which you can't see because you're looking straight at it, is a little piece of metal coming out of the oscilloscope, and it says CAL calibrate 0.5 volts, which means if you clip this lead onto the red lead here onto the signal lead onto that, you will get a signal that's 0.5 volts peak to peak, and it's a square wave. So this is 0.5 volts, and it's peak to peak. And if you adjust it so that we can freeze it, and I'll talk about that next, then you can see that square wave on the screen flashing by many times, but in the same place, so it looks like it's just sitting there, which is what we want. And the reason we have this is to calibrate or check the calibration on the oscilloscope. If it's perfectly calibrated, then indeed each one of these squares, which one of these divisions, centimeters, depending on where this knob is set, is going to be what it says it is. So if you switch the black knob up to pointing to 0.1, then each one of these centimeters, if it's calibrated properly, and that's what you're checking, is going to be 0.1 volts. So if this is set on the 0.1 volts per centimeter scale, and that's 7 centimeters tall, then it's going to be 0.1 times 7, or 0.7 centimeters. That's how you use this oscilloscope in terms of the vertical direction. We can also measure using the time scale and see if it's calibrated. There's another calibration knob here. Turn it fully clockwise till it clicks, and supposedly it's calibrated to these settings. Right now it's on 0.5 millisecond per division, so that means times 10 divisions, it's going to take 5 milliseconds, 5,000ths of a second, to go from one side to the other on the screen, which is much faster than you can see normally. But again, if you can freeze it on the screen, it looks like it's just sitting there. Okay, so that's where this is set right now. These are set at the 5 volts per centimeter scale here. So this is, if this is what you're looking at and it's 7 centimeters tall, that's 35 volts. If you're looking at channel 2, it's set at the 0.5 volts per centimeter scale. So if you had a pattern that looked like this, 0.5 times 7 is 3.5 volts high. So it'd be 35 volts if you're looking on this scale. It'd be 3.5 volts if you're looking on that scale. So that's how you calculate the amplitude, voltage of the amplitude. Okay, that gets to this little section over here. This is the section that's a little bit confusing. We're not going to get too involved in it. You can trigger the pattern going across the screen by plugging an input here that will trigger it in synchronization with whatever your signal looks like. We're not going to do that. This switch here is up at internal, INT internal. That means it's going to trigger internally depending upon the voltage at which you set it to trigger. If you flip this down to the bottom and connect something in here, that means you're externally triggering it with whatever you have externally to trigger it at whatever voltage you want. So flip this to internal, flip this to auto, and then this little dial here actually adjusts, there's a little minus sign, a little plus sign, it adjusts the voltage at which it triggers. It could trigger at this voltage, or this voltage. And so you can adjust that to the voltage at which it sweeps across the screen again and again and again, and forms a nice frozen pattern on the screen. So adjusting this knob here will freeze the pattern on the screen if you adjust it to the right voltage. And don't forget, you've got to adjust it depending on which channel you're looking at. If you're looking at channel 2, then you can adjust it to a voltage on channel 2. If you're looking at channel 1, you flip the switch up to channel 1, and then you're adjusting your freezing voltage on channel 1. So if you're not getting it adjusted, check this and make sure you're triggering it on the correct channel, channel 1 or channel 2. So that explains pretty much what's on this faceplate. And we'll take a look at this and we'll operate this in a real oscilloscope in just a bit.